Hi guys, Kenna here. So today we're going to go ahead and start a new unit. We're going to be looking at energy. We'll talk about all different forms of energy, but we'll focus primarily on energy conversions, especially with respect to gravitational energy, because that relates to what we've done so far in terms of mechanics, Newton's laws, etc. Okay, so let's go ahead and jump right in. Number one, what is energy? Okay, this is a basic thing, and this is going to relate to the concept of work and power, which we'll talk about a little bit later. Number two, what are the differences between potential and kinetic energy? Now, if you know those two words, you probably already know the main difference between them. All right. Number three, what is the law of conservation of energy? That word conservation is important here. And what does that mean in terms of the universe energy, universe and its energy? Okay, so let's move on to the next one. Number four, and this ties back to number three in the law of conservation of energy, and when we have energy conversions. And again, I'm going to try and use a lot of our examples from astronomy because that's something that got me interested in this, and we'll talk about how that works. But number four, what is the role of thermal energy in the law of conservation of energy? And how does this relate to entropy? Okay, so entropy is going to play a big role in terms of how the universe deals with the law of conservation of energy. And lastly, what is the difference between renewable and non renewable resources? And while this is not directly a physics problem per se, this ends up being important in terms of how we approach energy conservation with respect to our planet. And so we'll briefly talk about it here. Okay. All right, let's jump right in. So before I even get started, I want you to kind of pause and write down a definition for energy. What do you think energy is? What does that mean? So pause the video here, write that down, and then let's go ahead and continue. Okay, so you hear energy as a sound, you see it as light, you feel it as wind. Living organisms need energy to grow and to move. Every part of your life, every aspect of your life in some facet relates to energy. Okay. You use energy when you hit a baseball, when you compress a spring, when you lift a grocery bag. These are all examples of energy because energy is the ability to do work. Okay. And that's going to end up being a key facet of what we're going to look at today, the ability to do work. And I know we haven't done the physics definition for work yet. We'll do that a little later. But this ends up becoming a very key understanding with respect to how this whole process works. Energy is in everything. Okay. We do everything because of energy. If any of you guys had me for biology, you know the term I always used was, oh, so we've got this ATP available and we use this to walk, talk, think, and blink. Okay. Every action you take, every movement your body makes is going to be based on the availability of energy. You may have talked about aerobic versus anaerobic respiration. Where do we get that energy? From the food we eat. How do we get it there? We use it by mitochondria, by breaking it down. When you make a jump shot, you're using energy to turn the muscles on so that they can actually cause you to jump, so that you can flick your fingers and launch the ball towards the rim. When you bake cookies, you're using energy that's come through your electrical lines. You're using that or gas energy to go ahead and power a stove, which is going to go ahead and bake the cookies. Even down to sending astronauts into space is done with the use of energy. It's there. We make everything function because of energy. Now, the single largest source of energy that I can think of is the energy released by a supernova. Now, many of you have probably seen some of these nova episodes or something on the Discovery Channel where they describe the life and death of stars, and you've seen these computer generated images of a supernova. They are massive and capable of destroying a nearby solar system in just a few hours. A supernova is one of the greatest concentrations of energy we've seen in the universe. Here's just one example of a computer simulation of this type of energy. It's incredible the amount of energy produced by a supernova. Okay. All right. So as we continue to talk about energy, we need to keep in mind that energy is the ability to do work. And the combination of energy and matter in the universe is related to us by Einstein. Matter is the substance, and energy is the mover of substance. And the relationship between the two is in the form of E equals mc squared. Okay. Energy is the change maker. Anytime something changed or altered, when we start thinking of applying a force in terms of Newton's laws, when we talk about an acceleration, when we talk about a velocity, this is only possible because of energy. And it comes in two primary forms, either potential energy, which is our stored energy, or kinetic energy, which is the energy that's currently being utilized. So in physics, when we say potential energy, we're talking about energy storage. Now, in many cases, and what we're going to typically refer to in this unit is going to be the energy stored because of its position. We would talk about a spring being compressed, waiting to be released. That's stored energy. We can go ahead and talk about chemical stored energy in terms of the food that we eat. We can go ahead and talk about lifting a book above our heads and that having stored energy of position, because when we release it, it's going to fall. Now, it's not always going to be mechanical energy and can be plenty of different other forms like the chemical energy I just mentioned. But we're typically going to be referring to what we call GPE, or gravitational potential energy, which depends upon the height and weight of the object. Now remember, weight, okay, weight is a force. This is going to be the mass times the acceleration of the gravitation for that particular planet. We times that by height to give us our new unit, a Newton meter. So what are some examples of potential energy? We store water behind a dam because I can turn turbines, which can go ahead and produce kinetic energy. We pick a hammer up over our head. When we drop it, it's converted into kinetic and can create force. The food on our plate that maybe you ate for breakfast, maybe you're going to eat for lunch, just did. Okay. These are all examples of potential energy that we are trying to unlock to produce kinetic energy, which is your energy of motion. The faster the object moves, the more kinetic energy it has. Okay. Kinetic energy depends on both mass and velocity in the relationship Ke equals 1/2 mv squared.
Answer me! Hello? This is your cell phone!
So the unit we get here, mass velocity squared, is a kilogram meter squared per second squared, or a Newton meter, which is also known as a joule. So the unit we're going to be using when we measure energy is joules. And so you actually see this sometimes when you look at things like air conditioners. They'll give you a unit in how much it cools, how much energy it takes. You can see this with certain types of heaters, especially when you're dealing with things coming from Europe. But there are lots of examples of kinetic energy, flowing water, falling hammer, electrons, regenerating ATP in a biological cell. So there are a whole slew of forms of energy. There are five main forms of energy that we kind of look at. We have gravitational, which kind of we'll focus on. Mechanical, which actually has a couple of subcategories: stored mechanical, motion mechanical, so that's kinetic, your nuclear energy, chemical energy, these fall into this category. You've got your electromagnetic energy, which is your electrical, your sound, your radiant. And then lastly, and this is definitely not one to overlook, and that's number 9, the thermal energy, which is heat energy. And then we'll talk about this with respect to entropy here in a little bit. So gravitational energy is the energy because of position of an object. You lift something up really high off the ground, And it's got this stored gravitational potential because when you release it, it's going to go ahead and fall to the earth because of gravity, and that's going to give it some sort of kinetic motion. All right. The next one is stored mechanical energy. We were talking about springs earlier. You can do this with anything that's got some compression to it, but by applying a force, you can compress something, and that gives it stored mechanical energy that when you release it, it's going to bounce back out. Okay. So it must push or pull to go ahead and get that stored mechanical energy. The next one I want to cover is nuclear energy. So, nuclear energy is the energy that's stored in the nucleus of the atom. That's where the term nuclear comes from. Now, remember, we talked in your biology classes about the fact that in terms of chemical energy, energy is stored in the bonds. Well, in this particular case, the energy is also stored here in the attractive forces between the protons and the electrons. Okay. So while the nucleus of atoms splits, this energy that's stored in these attractive forces is also released. So this is a form of potential energy as well. And this is probably the most concentrated form of energy. And when we talk about nuclear energy, we usually talk in terms of nuclear fission, which is the breaking apart of atoms, or nuclear fusion, which is the combining together of smaller atoms to make bigger atoms. In both cases, we're dealing with the creation of stored energy or releasing that stored energy. Then we get to what we would traditionally call more traditional chemical energy. So, this is that energy in the bonds that we talked about in your biology classes. When you digest your food, you are using the energy from that food in the form of breaking its bonds. Okay. So, when these bonds are broken through a chemical reaction, okay, these are exergonic reactions or energy releasing reactions that are going to go ahead and provide energy to create your ATP for you to function. Well, we also can do this in terms of things like combustion reactions. When you burn fossil fuels, you are breaking the bonds inside those materials to go ahead and release the energy of those bonds out in terms of producing power. And then we deal with mechanical energy. This is typically going to be in the form of motion, water powering a water wheel or coming down a waterfall, what you'd see coming off a dam, wind power. These are a lot of the things that we're trying to harness in terms of more renewable energy resources we'll talk about later for a greener environmental impact because they're very renewable. I mean, they keep coming without actually doing damage or destroying or breaking down things. Movement of vehicles, when we start looking at car accidents and taking off of materials like a sprinter running out of the starting blocks, we're talking about mechanical energy. Sound, blood traveling through your body. These are all examples of movement. And so this is a form of kinetic energy. Then we get electrical energy. This is what's running through your electrical system in your house when you plug into a wall outlet. This is the kind of energy you're getting from the movement of electrons. And so, as you get this moving electrical charge, you're starting to see that we can do things with it. This is a great example of energy being used to do work. Okay. When you go ahead and start taking a look at how you use your phone, when we go ahead and turn on a light, obviously that's energy coming from somewhere. Those electrons are moving, providing heat, light, sound, whatever it is coming out of that particular appliance. Now, a lot of us don't think about sound energy as being energy necessarily, but you're constantly being bombarded by it in your day to day life. And that energy is being transferred in the form of these compressional waves, or what we call longitudinal waves, which we'll talk more about next term. And this vibrates on the tympanic membrane inside your ear, and that produces the auditory induction process that goes ahead and lets us hear sound. Okay, so again, this is a movement, so this is going to be a kinetic energy. We can also talk about radiant energy. This comes from electromagnetic radiation. This can transmit through space. And light, as we used to see, is a form of kinetic energy from radiant energy. All the different wavelengths, everything from, microwaves, X-rays, radio waves, up to the higher energy forms when we start looking at gamma rays. Okay. And lastly, Um, this is one that I think gets overlooked a lot. I mean, not that you don't think of it as a form of energy, but that it's an important form of energy that's going to come back in many different instances throughout this unit. This is the internal energy of a substance due to the vibration of its atoms. Okay, that's what heat is. Cold is not a thing, it's simply the lack of heat, okay, lack of thermal energy. And so that's about the average kinetic motion of the particles within a substance. And we'll definitely talk about this more next term. Okay. Friction can cause thermal energy, any change in the state of matter. We'll go into more details next term. All of this leads us up to this idea of the law of conservation of energy. This is a key one. Please make sure you take away this concept from today. Energy cannot be created or destroyed. However, it may be transformed from one form into another, but the total amount of energy never changes. Okay? Energy will always transfer from a high form to a low form, and no energy transfer is 100% efficient. So I'm going to introduce this to you right now, but this is a concept that will come in big later on when we get into next term. Okay? When we start talking about energy never created nor destroyed, how can we get organization or reorder or disorder if everything's always moving to a point where it's less organized? Well, here's what we mean. We typically look at something in terms of systems. We have the system that we're identifying, that we're observing, and everything else outside of that is what we would call the surroundings. And because energy is neither created nor destroyed, what we have to realize is that if we lose energy from the system, that energy is being transferred to the surroundings. If we gain energy into a system, it came from the surroundings. It doesn't come from a vacuum from nowhere. The energy that's going to be here is here. We're just changing the form of it. So, this concept of system and surroundings is going to be crucial as we continue to move forward in terms of our understanding of energy, but also as we start looking at thermal energy and other concepts related to this as we go ahead and move forward. Okay, good. So, law of conservation of energy can't be created or destroyed. However, energy is transferred. And when we go ahead and look at these types of transfers, one of the most common examples that we typically use is that of gravitational potential energy. Now, remember, gravitational potential energy is what we call GPE. And this is equal to mass times gravity times height. And we can convert that gravitational potential energy into kinetic energy, which we gave you the equation for earlier, 1/2 mv squared. Okay, so keep these in mind as we go ahead and show you this example. Now, if you have ever been on a roller coaster, most of you have, maybe some of you haven't, you definitely feel the energy that's involved in the roller coaster. And so in this particular demo, I'm going to show you, watch the numbers in terms of the height, the speed, and then the bars on the right are going to go ahead and show you kinetic energy, potential energy, and total mechanic energy. Okay. So watch the roller coaster car as he goes down, the speed picks up. As he picks backs up, you have more kinetic energy, less potential. As you go up around the loop, you build up potential and lose kinetic. And the same thing happens in the smaller loop. When you go up a hill, you gain potential and you lose kinetic, and so on and so forth as you continue to do this. And so the relationship is that as you lose potential, you gain kinetic. Energy can't be created or destroyed. And so if you can find the total energy in a system by an object at a certain height to begin the whole process, we can consider that a system and the total amount of energy. And if we can calculate the potential energy at any point in time, we know that the rest has been converted into kinetic energy. This is a form of what we call an energy conversion, where we change one form of energy into another form of energy. The most common example is the one I showed you on the previous slide when we go ahead and start looking at uh, kinetic and potential. But, we can also look at this in terms of other forms of energy. We can look at chemical being converted into mechanical when we start thinking about eating and that energy being converted into the movement of our muscles. So there's a lot of potential examples here. If any of you have ever watched skaters on a half pipe like this, okay, this is a great example of that kinetic versus potential conversion. As the skater rolls down through the half pipe, he's building up speed. Then he starts going up the other side. He loses that speed, but as he loses it, he's gaining potential energy. Now, of course, this is not a perfect example. Most real life examples aren't. Some of that energy is going to be lost. And this is an important thing to take into account. That energy is lost is typically lost in the form of heat, thermal energy. And that is typically not able to be reclaimed from a system, and that's due to an inefficiency. And we'll talk a little bit later about mechanical advantage and mechanical efficiency once we start really getting a handle on understanding how kinetic and potential energy work. Okay. Another good example of this is a pendulum. Okay. As it swings up to one side, it's building up potential and it's losing kinetic. When it gets released, that potential is converted into kinetic energy until it gets up to the peak at the other side where it's been converted back to potential energy. At any point in time, if we assume we don't lose any energy due to drag, resistance, sound, these types of things, then what we have is a closed system where PE is converted into KE, KE into PE, and vice versa. One of the examples that I want you to be able to do by the end of today is to go ahead and be able to convert potential to kinetic. And this gives us a great example. In this particular instance, we have the individual standing on top of that high platform. All of his energy is potential energy because he hasn't jumped. But as he jumps, that potential energy is converted into kinetic energy. And if we can measure his height at that point, we can go ahead and tell how much he still has in terms of potential, subtract that from the original, and know that the rest of that energy has been converted into kinetic energy. All right. This again is because of the law of conservation of energy. Now, energy cannot be created or destroyed. However, according to Einstein, if matter is destroyed, energy is created. And if energy is destroyed, matter is created. And the perfect example of this is you. Okay? The total amount of mass and energy is still conserved in the universe. But when you go ahead and eat chemical energy, you are converting the energy in those bonds into energy inside your body to build up you. You are, remember, what you eat. And so the energy from the food that you eat and the building blocks that come from the food that you eat are converted into your actual raw materials. So when you eat that chicken breast, you actually are taking the carbon out of those molecules and using it to build up your cell tissues. Okay? This all is related to each other through Einstein's famous equation E equals mc squared, where E is energy, m is mass, and c is the constant for the speed of light. Okay? Obviously squared. And so this is a complicated thing, part of general relativity. If you want more information, please don't hesitate to go ahead and look it up online or come ask me and we can talk some more about it. So what are some other energy transformations? Well, if you've ever struck a match, you've got stored chemical energy in that match head. You use some friction to ignite it, then that combusts and burns. There's a lot of energy transformation going on there. If you've ever used a battery, a photovoltaic cell, right? We are converting the chemical energy inside the battery into electrical energy to power our devices. Living systems, photosynthesis is a great example of energy transformation. We're converting light energy into chemical energy to be used as energy for food later on for both the plant and for those things that eat the plant. The movements of the winds in the Gulf Stream, okay, we can use that to push air masses to go ahead and push clouds. We can use it to power turbines. The interior temperature of an organism as it changes. Okay, now we as humans would like to regulate internal body temperature, try and keep it very stable. But when we try and do that, we are changing things in our environment. You sweat, and that sweat is going to go ahead and take some heat away from your body. And as it does so, it releases that energy into the surrounding environment. Okay. If you're cold, you shiver. You are causing a movement of the muscles. That friction creates heat that comes from the food that you ate, converting chemical energy into the energy of movement. These are a lot of good examples. So, the chemical energy in the food you eat is converted to chemical energy your body can use. Remember, in your biology classes, we talked about ATP. Your body then converts that chemical energy into kinetic energy so that you can walk, talk, think, and blink. And your body uses it and keeps eating, and this process goes on. You lose some of that energy through inefficiency in the form of metabolic heat, which is a form of thermal energy. So let's take a look at an example with riding a bicycle. For your bike to start and keep moving, you must transfer energy and convert it to move your legs. As you move your legs are moving the crankshaft, okay, the pedals. As that goes ahead and turns the little rotary, that's going to go ahead and cause the chain to go around, which impacts the gears on the back, and that's going to go ahead and cause the tire to move. Okay. So number one, chemical energy in your body is converted into kinetic energy when your muscle fibers contract and relax to pedal a bike. Two, your legs transfer this kinetic energy to the pedals by pushing them around in a circle. Three, the pedals transfer this kinetic energy to the gear wheel, which transfers kinetic energy to the chain. And four, the chain transfers the energy to the back wheel, which is actually what causes the bike to move, only possible because of the friction that exists between the ground and the tire of the bicycle. Now, remember the law of conservation of energy. Energy cannot be created, cannot be destroyed. However, remember it can be converted from one form to another, as long as it always adds up to the same amount of total energy. We now know that energy is not lost, even though it seems to be, but instead is converted into unusable heat. And this movement towards a greater and greater disorganization in the overall total amount of energy is what we call entropy. And we'll talk a little bit more about this next term as we get into this concept of entropy and we start looking at things like Brownian motion. Okay. Remember that while we talk a lot about mechanical efficiency and the fact that there is no lost energy, it's not lost in the truest sense, it's converted to heat, but for all of our calculations, we tend to overlook this. It's kind of like neglecting air resistance that we did early in the year. Okay. But there's always a certain amount of that energy which gets lost in terms of its conversion into thermal energy, typically due to friction. And remember, this is not useful and is actually a form of entropy. Now, these are the old incandescent light bulbs. They light up because it causes the electrons that are moving through it in terms of electricity to slow down as they go through the filament, and the filament heats up. Okay? When it heats up hot enough, it begins to glow, producing light. But we lose a ton of energy from the light bulb in an incandescent light bulb in the form of heat. So if you look at like an LED light bulb, they're far more efficient. They have very little heat, mostly just produce light. And that's from LED light emitting diode. We'll talk about these things more when we get into electricity next term. Now, except for nuclear power, all of Earth's energy comes from the sun. And this is because all other forms of energy come from plants harnessing the sun's rays in the process of photosynthesis. So when we start thinking about things like fossil fuels, for example, fossil fuels are the remains of plants and animals who got their energy from where? Either eating other plants or from the sun itself. And so you can trace all of the energy pretty much on our planet back to the sun. All right. Okay. So we want to kind of finish out talking a little bit about renewable versus non-renewable. I know this is not a strictly physics topic, but I think it's valuable to go ahead and cover again, although I'm sure you probably got it in middle school already. Renewable energy sources include solar energy, which comes from the sun, can be turned into electricity, heat, wind, geothermal, um, biomass, hydropower. These are all examples of renewable resources because there's not likely to be any running out of the supply. We used to think that nuclear came into here, but then you start realizing about how nuclear reactions work. If you're doing fission, which is all we've been able to accomplish here on Earth, when you do that, you're releasing a ton of energy, but you're doing it by actually breaking down the atoms themselves. Well, what's going to replenish those atoms? As you use them up, they're not coming back. So we now move this one over to the next category, which is going to include our oil, natural gas, all these fossil fuels. Okay, because remember, those are in limited supply. They're manufactured by dead and dying plants and animals in just the right conditions that form oil, water, excuse me, not water, oil, natural gas, and other forms of petroleum. And then we go ahead and include here um, nuclear reactions, things like the element uranium, whose atoms we split, because once you use it, it's gone. Last thing for today, let's do a little bit of practice going ahead and taking a look at kinetic energy. All right. So, what is the kinetic energy of a 1 kilogram mass moving at 4 meters per second? Okay, do you guys remember how to go ahead and do this? Okay, so if we're looking at kinetic energy, the equation that we're going to go ahead and use is Ke equals 1 half mv squared. We've got our velocity here, we've got our mass here, so we simply have to solve. So in this particular instance, 1 half times the mass, 1 kilogram, times the velocity, 4 meters per second squared. 4 times 4 is 16, times 1 is 1. Times 1 is 16. Divided by 2 is going to be 8. And so hopefully you were able to follow that math through as we went ahead and did it. And we can end up getting 1 half mv squared to yield 8. Now remember, our unit here is a joule, and a joule is going to be a kilogram meter squared per second squared. Or if you remember, we have the Newton, which is equal to a kilogram meter per second squared. And so we add another meter, so the Newton meter or the joule. Okay. Okay. So let's try one more. What if the mass was going in the opposite direction? Minus 4 meters per second squared. Now, hopefully you recognize that the math really isn't going to be any different. And the reason for this is that Ke equals 1 half mv squared. That squared is important here. So we go ahead and do this. 1 half 1 kilogram times v squared minus 4 meters per second. But we're squaring it. Minus times a minus is positive. So that's going to be 16 times 1 is 16 divided by 2 is 8 once again. So when we start looking at joules, okay, because it doesn't matter what direction it's moving, it's still using the same amount of energy, okay, because it's the same mass that's being moved. So kind of keep that in mind as you're going to go ahead and go through. Well, that's all I've got for you guys today. I hope you take care of yourselves, stay healthy, stay well, and I'll talk to you soon. Have a great rest of your day.